Every diagram you've ever seen of what lies beneath Yellowstone, every textbook illustration, every documentary graphic showing a column of molten rock shooting straight up from the depths of the earth was wrong. Not slightly off. Wrong about the actual direction the heat is traveling. A team that just built the most detailed underground model of the western United States to date found something far stranger and considerably closer to the surface than anyone had previously sketched out. Before getting into what's changed, it's worth clearing up a common misconception about what Yellowstone actually is. Yellowstone isn't a mountain. Picture a volcano, and most people imagine a cone with an opening at the top. Yellowstone has no cone at all, it's a hole. A caldera, roughly 30 by 45 miles across, so vast that standing inside the park, photographing elk, or watching the hot springs bubble, you can tell you're inside a giant crater. The rim disappears past the horizon in every direction. A caldera doesn't form when the ground explodes outward, it forms when the ground collapses inward, because whatever was holding it up from below has since pulled away. Yellowstone has done this twice in the last 2 million years, once around 2. So time 1 million years ago, and again roughly 63,000 years ago, each time ejecting somewhere between 1,000 and 2,500 cubic kilometers of rock ash and magma. For scale, the 1980 eruption of Mount St. Helens, the one that flattened forests and dominated headlines for weeks, released about 1 cubic kilometer of material. Yellowstone's past eruptions were roughly 1,000 times larger. Anything that tops 1,000 cubic kilometers earns its own classification as super eruption. Only about 20 places on Earth are even geologically capable of one. What makes these events so consequential isn't the crater itself, but the ash and sulfur they hurl into the atmosphere afterward, enough to dim sunlight and cool the planet for years, disrupting agriculture globally. That's the system this new research set out to understand more precisely. Start with what most people already believe about Yellowstone, because that belief has to be dismantled before anything else makes sense. For about 50 years, the standard explanation for what powers this supervolcano was something called a mantle. Plume. Think of a lava lamp. Heat the base and a blob of hot wax breaks loose and rises straight up in a column. The old theory proposed something similar. A plume of superheated rock rising from deep near the planet's core, burrowing upward through the crust like a blowtorch aimed at the underside of North America, held in check by a caprock layer until it found a weak spot to break through. That idea had one strong point in its favor. Yellowstone sits in a genuinely odd location. Nearly every volcano you can name sits near a tectonic plate boundary somewhere along the Pacific Ring of Fire, where plates are colliding or pulling apart. Yellowstone sits in the middle of a continent 1,000 miles from the nearest plate edge. A blowtorch rising from deep underground was the obvious way to explain a hot spot in the middle of nowhere, with nothing at the surface to account for it. But the theory had a problem that quietly nagged at geologists for years without ever getting resolved. A plume predicts a narrow, focused column of heat, essentially a single hot point rising cleanly from below. What scientists actually measured underneath Yellowstone looked nothing like that. For years, the mismatch sat there as an uncomfortable footnote. Because nobody had the computing power or data resolution to fully work out what was really going on, researchers knew something didn't add up, but couldn't yet prove an alternative. So the plume model stuck around mostly for lack of anything better. That changed with a new study published in the journal Science earlier this year, led by a research team that included geophysicist Liu Lijun, working with the Institute of Geology and Geophysics at the Chinese Academy of Sciences. The team built a high-resolution 3D simulation of the entire western half of North America, modeling both the planet's rigid outer shell and the softer, slower layer beneath it. They ran the simulation forward using present-day physics and checked the results against decades of independent geophysical and geochemical data already collected at the site. What came out was not a rising column of heat at all. The heat. Feeding Yellowstone isn't coming from directly below, it's arriving from the side. To understand why you need 2 layers. The lithosphere is the planet's rigid outer shell, the crust plus the very top of the mantle, cold, brittle, and essentially solid. This is what people usually mean by tectonic plate. Underneath it sits the asthenosphere, technically still rock, but hot enough that over long stretches of time it behaves almost like glacier ice, solid to the touch in any given moment, but capable of slowly flowing and deforming. Over thousands or millions of years, the way a glacier looks frozen day to day, but has clearly shifted when you compare photos taken decades apart. The new model shows that this deeper layer isn't sitting still beneath the western United States, it's flowing horizontally, sweeping steadily eastward at a pace of a few inches a year. Slow by human standards, but enormous over geological time, researchers are calling it an eastward mantle wind, borrowing weather language to describe something made entirely of slowly creeping rock rather than air. What's actually driving that flow is, in a sense, a ghost. Tens of millions of years ago, an ancient slab of oceanic crust called the Farallon Plate was sinking beneath western North America as part of ordinary plate tectonics. That plate vanished from the surface long ago, but remnants of it are still sinking deep under the middle of the continent today, and that ongoing descent is still steering the mantle flow above it. In other words, the volcanic system currently sitting under Wyoming is partly fed by the lingering wake of a tectonic plate that stopped existing at the surface an extremely long time ago. Here's the genuinely clever part. The flowing mantle, rock is hot, but it isn't liquid on its own. So how does it eventually melt and feed a volcanic system? The answer isn't that heat gets added. It's that pressure gets taken away. Picture a sealed warm can of soda, no bubbles. Not because the carbon dioxide isn't there, but because pressure inside the can keeps it dissolved. Crack it open, and it foams instantly without any added heat. And without anyone shaking it, dropping the pressure alone was enough. Deep underground rock behaves the same way. Under enough pressure, rock stays solid even at temperatures that would obviously melt it at the surface. Let that rock rise even a small distance, and the pressure holding it together eases. It can melt right where it is with no extra heat. Required. Geologists call this decompression melting, and it turns out to be the actual mechanism feeding Yellowstone rather than a straightforward surge of heat rising from below. This is also incidentally the same basic process that drives melting beneath mid-ocean ridges elsewhere on the planet. Not some exotic mechanism invented to explain Yellowstone, but a well-understood process being applied here in a new context. Put the two pieces together. The mantle, wind sweeps eastward, gets nudged gradually upward as it travels, decompresses along the way, and starts melting near the top of the asthenosphere, relatively shallow compared to the old plume model which placed the source far deeper near the core mantle boundary. The furnace powering Yellowstone was never a narrow, mile-wide chimney running straight down to one deep source. It's closer to a sideways draft of hot rock that partially melts itself simply by rising as it moves, a genuinely different physical picture from the one taught in classrooms for decades. That eastward mantle wind doesn't just carry heat along quietly underneath everything. It physically pushes against the thicker, colder lithosphere to the east of Yellowstone. Meanwhile, lighter, more buoyant material to the west pushes back the other way. The result is two opposing forces acting on the same slab of rock from different sides at once, stretching the plate caught between them. Picture pulling a piece of taffy or a stretch of pizza dough between two hands. It rarely snaps cleanly like glass. Instead, it thins gradually in the middle, weakens further as the pulling continues, and eventually tears open along its thinnest point. That's essentially what this new model suggests is happening and has been happening for a long time. To the lithosphere beneath Yellowstone, it's being stretched thin and torn open. That tear becomes an actual channel, a pathway that lets melted rock migrate upward far more easily than it ever could by pushing through a fully intact plate. It also explains the oddly lopsided underground shape scientists have measured for years without fully understanding it. It was never a single point, the way heat under Hawaii forms a narrow, focused hotspot from one concentrated source. It's a seam, a long tear stretched across a significant distance in the lithosphere, which is why the heat signature leans toward the southwest, instead of sitting as a clean, centered column the way older diagrams always showed it. This picture essentially rules out one of the most persistent popular images people carry about Yellowstone, an enormous underground lake of glowing liquid magma, just waiting beneath the surface, ready to burst out at any moment. That lake, as commonly imagined in documentaries and disaster movies, isn't there, and based on this research, it likely never was. What actually sits beneath Yellowstone is something geologists call a magma. Mush, mostly solid crystalline material with pockets of liquid melt sitting in the gaps between crystals. More like a slushy than a swimming pool or wet sand, where the moisture happens to be molten rock instead of water. Crucially, you can't drain a slushy the way you'd drain a lake, and you can't pump one out through a straw either. It doesn't slosh around freely, and it doesn't surge upward on its own the way a body of pure liquid magma could under pressure. This mush is genuinely stiff and resistant to flowing. Its effective viscosity is many orders of magnitude higher than pure liquid magma, which means it doesn't erupt easily under ordinary conditions, and it directly challenges older assumptions about buoyancy alone driving an eruption. A body of truly liquid eruption. Ready magma appears to assemble only briefly shortly before an eruption, rather than sitting fully formed for centuries waiting for a trigger. So what does this mean for eruption risk? The question most people actually want answered. To be direct, This finding doesn't mean an eruption is coming anytime soon. The researchers involved don't believe Yellowstone is somehow overdue, and nothing in the new model points to an imminent supereruption. If anything, the fact that eruptible magma only assembles shortly before an eruption, rather than sitting continuously in a huge ready reservoir, is arguably reassuring in the near term, since it means the system spends most of its time in a state that resists erupting rather than sitting on a hair trigger. But flip the same finding around, and it introduces a real complication worth taking seriously. The classic warning sign everyone's been told to watch for a giant magma chamber, slowly and steadily filling over centuries, building visibly toward some kind of climax that monitoring stations could track well in advance, may simply not be how the system behaves. If that's true, the old monitoring assumption may not hold up either, and that matters for how we prepare going forward. Compare this to somewhere like Iceland, where researchers can directly track a magma chamber, refilling after each eruption, watching it approach roughly the volume it reached before the previous one in a fairly predictable, observable cycle that gives scientists real lead time. Yellowstone, according to this new model, doesn't appear to work that way at all. No one has ever actually observed a supervolcano the size of Yellowstone go through a full eruptive cycle with modern instruments, so there's no confirmed real-world template to compare this new picture against. That's not the same as saying an eruption is imminent, and it would be dishonest to frame it that way. It's something quieter and, in its own way, more unsettling. The monitoring community may have been watching the wrong signal all along, based on a model of the system that this new research suggests was fundamentally incomplete from the start. Now, for the part that genuinely made researchers sit up because Yellowstone hasn't stayed in one place throughout its history, and that matters for thinking about what comes next. Trace a line southwest from the park, and you land on the Snake River Plain, a long, oddly straight scar cutting across Idaho, visible on any topographic map of the region. That plain is essentially a trail of dead calderas, older versions of Yellowstone, that already finished their eruptive cycle and went permanently quiet, each one marking a previous stop along this hotspot's long march across the continent. This underground hotspot has been burning its way northeast across North America for roughly 17 million years, leaving a trail of collapsed, extinct calderas behind it. As it moves Wyoming, where Yellowstone sits today, is simply its most recent stop, not a fixed permanent home. For that entire 17 million year journey, the system has been burning through crust that was relatively warm and comparatively thin, an easy target for melt to push through without much resistance. Directly ahead of it to the east, though the crust changes character, colder, harder, and considerably thicker than what the system has moved through so far, nobody's claiming anything dramatic is imminent because of this, but it does raise a genuinely open question with two very different possible answers. And researchers admit they can't yet say, which is more likely a thicker, colder lid ahead of the hotspot's path could smother the system over time, letting heat spread sideways instead of concentrating anywhere, gradually causing the hotspot to lose steam and eventually go quiet as it runs into terrain that resists it. Or that same thicker, colder lid could act the way any lid does on something building pressure underneath heat and melt that previously had an easy path upward through thinner crust might lose that outlet. And pressure that used to dissipate freely could behave very differently once it meets tougher material overhead. Right now, researchers genuinely don't know which outcome is more likely. That's the honest, somewhat unglamorous, and admittedly slightly unsettling state of current understanding. As one of the paper's authors put it, the underground plumbing is simply different than scientists previously assumed, which means every existing model used to plan for a future eruption now needs to be rebuilt to account for this new picture. Step back for a moment, because this says something bigger than just one volcano. A team of researchers ran detailed new modeling on what is almost certainly the single most heavily studied volcanic system on the planet, a site with more seismometers, more monitoring instruments, and more published research attached to it than nearly anywhere else on Earth, backed by decades of accumulated data from an enormous scientific effort. And the standard textbook picture, the one most people have carried in their heads for decades, drawn in nearly every documentary and popular science article about the site, turned out to be pointed in the wrong direction entirely. Not slightly imprecise. Wrong about the basic geometry of the system. Scientists thought it rose straight up from deep below. It's actually moving sideways, fed from an angle nobody had properly accounted for. The most important part of this story isn't that Yellowstone is somehow scarier than people assumed, if anything. This research leans toward the opposite conclusion about near-term risk. It's what this reveals about how much confidence was actually justified in the first place, about one of the best studied geological features on the planet, Researchers had already sensed something didn't quite fit about the old description long before this new model came along to explain why the numbers never lined up. No one can directly observe the interior of the planet, drill down and take a look, or pull up a live camera feed of what's happening miles beneath the surface. Everything we know about the enormous machine beneath our feet comes from indirect evidence, seismic wave patterns, mathematical modeling, geochemical sampling, computer simulation, all of it necessarily provisional and subject to revision as better tools, more computing power, and better models become available. A few weeks ago, when this study came out, the physical ground underneath Yellowstone hadn't changed at all. Not 1 degree hotter, not 1 crack wider. What changed was the picture in scientists' heads of what's actually happening down there. And given how confidently the old picture was taught for 50 straight years in classrooms and documentaries around the world, that shift in understanding is genuinely worth paying attention to, even without a dramatic headline attached to it.